Hello everyone, my name is Joe Scorsone, channel is called Ethernet Wink. We got blue lights and you can read the title. So in today's video, you could tell we're going to be talking about C++ more again, and we're going to be doing more about pricing options. These videos have been doing great and they're a lot of fun for me to make, so I'm going to keep on making them until I've done all I can pretty much for making pricing models. In this video, we're going to be doing a chain and talking about implied volatility a lot. And the next two video ideas I have for this is going to be binomial option pricing model and Heston. If you guys have any other suggestions, please leave them down below. I'm kind of just milking option prices as much as I can because the videos are doing good and I hope that you guys enjoy them. Now, we're going to be building on last video's code. I'm probably not even going to put beginner friendly in the title of this video because I want to really talk about implied volatility, which is a chewy topic. And so I would rather keep this video a little bit more applied and mathy and chewy than go over what is an option. If you're totally new to this stuff, go to the last video I made and it'll explain everything a lot more in depth and you'll be able to understand this video a lot better. So, without further ado, let's get into the code, because like always, I have the code already written, and we're going to go over it, and I'm going to zoom in on it, because I like your eyes. So, we got this struct, just like the last video, and we're adding an attribute to it. Let me make my face a little bit bigger. There we go. We're adding an attribute to it. We're adding the market price. We're going to get more into that later, when we actually talk about implied volatility, and pricing, and all that fun stuff. Because, oh my gosh, if I don't keep myself on schedule, less than 20-minute video, I'll be sitting here for 45 minutes talking to you about mispricing options and how weird the whole concept is. Error function, cumulative standard normal distribution, just like last video, that's the same. Different function, Black-Scholes pricing function. This literally does what it says. It just returns the price for these parameters in the Black-Scholes model. Just the premium, not the Greeks. Find implied volatility. We're going to get into that. We're going to talk about this function a little bit more first, because this is what actually gets called. And a little cool idea, if you care, a cool thing to do could be to put all of these functions, really everything, into a class and only have this be the only public function. Could be a cool idea if you care, if you want to do it. Now, this is, if we go into the last video, or into the last thing. Oh, I changed it in here too. That's all right though. This is actually what gets called, and this is now going to return a vector of contracts. In other words, the option chain, not just information about one contract, but we're going to go and we're going to iterate through, right? And it's going to spit out, this is 10 contracts? Does it actually, 9 or 10? Because it's -5, less than 5. So it would be, but we have to do 0 as well. I think it's still 10. I really don't know. That looks bad. Regardless, we're still going to go through it. We're returning a vector, so we're returning an entire option chain for whatever kind of contract we want for these parameters. So we also have this random number generator, and we're doing it on a normal distribution with a mean of 0 and a standard deviation of 0.5. We're going to get into why we're doing this, again, a little bit later. Now, I'm sorry, I just knocked my microphone twice trying to itch my nose. But we're using a for loop, of course, because we're going to return a chain, so we need to do multiple contracts. And you see with this vector chain, at the end of it, whenever we finish calculating everything for a contract, chain dot pushback. So, starting it off, whenever we first start the for loop, we're going to make a contract. Sorry for that. I don't know why my keyboard does that sometimes. I have one of those. Oh, I'm not even full screen. There we go. But we're going to start making a contract. Calculate days till expiry, set that, set our strike price, right, because we're iterating through it. That's pretty much the only difference. It's always going to be k plus I. So we get information for a bunch of different strikes. Premium and intrinsic value, these don't change if it's a call or a put. And here we go. These 3 lines, right? simulate a market price with some noise, a random number from this generator. And we have a market noise, and we're setting an attribute. Market price equals gets premium plus market noise, and this number can be negative. What is that all about? And then we use that market price to find the implied volatility. Oh my gosh, what are we doing, right? Well, let's go into this function. Because the method to find implied volatility that we're going to use, and that's what's widely used, is called the Newton-Raphson method, right? So this method starts with an initial guess for implied volatility, right? We're setting this initial guess to be 0.2. We have a tolerance, how close to a number, how close to the number we want to get, and a max iterations. We're doing 100 right here, chose that arbitrarily. Now, for every iteration that we have, we're going to price an option using the Black-Scholes model like normal. When we first start, it's going to be this first initial guess. Then we need to get our vega. If you don't remember from the last video, vega is the Greek that represents how much the option premium will change for every 1% change in implied volatility. That's why it's so important that we use vega to model implied volatility. What is implied volatility as well? Let's get into that. Implied volatility is the market's guess of future volatility, right? Because options, the premium for an option will go up if future volatility is expected to be higher. That's why options always juice ahead of earnings. If you've ever bought an option contract before an earnings call and the earnings came out and it was in the direction you wanted, but your option still lost money, that's why. They just always juice because everybody knows implied volatility will be higher because of earnings. So implied volatility is already inherently juiced when you buy the option. Don't buy options before earnings, or if you do, sell them before the earnings. Or price them properly, regardless of what you're trading. So we're going to use this vega, we're going to get this vega, right? And then we need to say price difference, which is the market price that we got before minus the price. What does this talk about market price, Joe? Isn't the price the price? No. You would think it is. I thought it was for the longest time. But so the way I like to think about it, the terminology I like to use, is we have our perfect price, even though the Black-Scholes model isn't perfect. We have our perfect price, and then we have our market price. What's the difference? Well, market price is the price of the option as a result of market participants. Because it's like anything else, it's worth as much as people want to pay for it at the end of the day. So if a contract is really worth $1, someone's willing to pay $1.50 for it, all of a sudden it's worth $1.50, regardless of every fundamental and every pricing model. So that's what that market price represents. It won't be that dramatic of 50 cents. Sometimes it might be, who knows? But that's pretty much what it is. When there's more buyers than sellers on an option, the option will be a little bit more expensive. When there's more sellers than buyers, the premium will be a little bit lower. It's the intuitive way to think about it, but it's weird to think that that's actually how it works. It is. It's not actually a derivative. Isn't that terrible? But this is how it works. Because we have this price difference. And if the price difference is less than our tolerance, the super small number, we made it. The absolute value of it. We made it. Right? That's the accurate. We accurately modeled this market priced option. We accurately modeled it. And so then we can calculate the sigma for the actual implied volatility of that contract. And that's the Newton-Raphson step. It's like how speed equals distance over time, right? So if you know speed and you know time, you can find difference. Same concept, just that algebra before option contracts, right? So after we get to that, then we return sigma. Either we get to that or we just reach our iterations, then we return that value. And that is the contract's implied volatility. Then we add that contract to the chain. And there we go. This is the notation to make a for loop in C++ like this. If you didn't know, I didn't know before I did this, and I think it's awesome. I'm really happy that you can do that in C++. But I want this to be a little bit more of a coding video. So I'm going to make this bigger. I'm going to zoom out. so that way everything fits on the screen. I might have to make my face smaller. I'm gonna have to zoom out again. And I'm gonna clear, do that again. There we go. And oh, you really can't read that, can you? What if I zoom in again? Okay, that's fine. That works. I really hope that you can read that, because it kind of has to be this big. I can't read that when I'm looking at my OBS. I only have a script open this video, but when I'm looking at my OBS, I can't read that. I hope you can. I'm going to look at this, of course, afterwards. If you could see this, of course, I think you could read it. Regardless, we have a lot of different things now when we display it. I can actually show you up here. Oh yeah, if you could see that, then you could see this, yeah. So we have our strike price, of course, because we returned a chain. So all these, premium and market price. We're showing both of those things. And our intrinsic or implied volatility. That's what really matters. That's what we're going to really talk about. Because, pull up my wondrous art, because I already tried to record this video. If you're familiar with what a volatility smile looks like, it's what the implied volatility of the option chain should look like. So as you go from in the money to, that's a huge O, out the money, the IV does something like that. In the money, in the money, in the money, in the money, whoops. In the money, in the money, at the money, out of the money. It'll kind of make this little thing like that. And these contracts are at the money-ish and have the lowest IV. Normally the ones with the lowest IV are like the ones right outside the money, maybe 2 spots outside the money, have the lowest IV. Why is this important? Well, because this is what it should look like. However, sometimes you get discrepancies. Sometimes you get a world where maybe it looks like that, right? Maybe you got this little discrepancy. I'm going to make it dramatic. Because you're going down in the money, in the money, in the money, right? Picking up bunk, right? I'm going to make it dramatic. These contracts have super low IV. That's cheap, right? I want that. This contract, regardless of direction that I think the underlying will go, regardless of days to expiration, this is the cheapest contract relative to the other ones that are out of the money, right? So that's what I could ideally, inherently, probably make the most money on. So when we look at it, we're looking at calls right now. That's what should happen. Because it's a random number generator, these two, can you even see that? Yes, you can see implied volatility. Okay, good. Yes. So these two numbers should be higher because it's a random number generator. That's how I cheated a little bit. They're lower. But when we get to the at the money, we have this value, 20. And then, right, it keeps on going down, goes down a lot. And then by now, it should start picking up, right? And so this is 2 spots out of the money. We have a 19 IV when most of the other ones around it are in the 20s. So this is the cheapest contract on this chain relative to out of the money contract. So 101 to 104, because that's how far we go. This contract is the lowest IV. Right? And so now, when we look at our market price for the 102 call and our actual option price, we see a discrepancy. We see a difference in the market price to the actual Black-Scholes model option price. And it's one that would work in someone's favor. Because if you buy this contract at $9.16, and it should be trading for $9.42, before anything happens, you should make, what is that, 28 cents on this contract? Before anything, for free. Just because you noticed this, with no risk, you should make 28 cents on this contract. That is crazy. That's how you make stupid money trading options. You now even look at this one. Maybe you don't know this. You're just a regular average Joe. You work your normal job. You have a day off, so you're going to day trade a little bit. You got a tip from your buddy, whatever, and you're going to take these calls, right? you're going to take the 103s. You don't want to pay in the 9s. You want to pay below 9. Oh, it's below $9. It's cheaper, right? Actually, market price right here. So you would pay actually a little bit more. So that's a little bit unrealistic. But whatever. We're modeling this as best we can, right? But think about it like this. You're going to take the 103s for whatever reason. And you're going to pay, you're thinking like this. You're thinking, oh, this is one spot out of the money. It's the same thing. So if the stock moves closer to the money, I should make way more than this guy, right? Because it's already closer to the money like that. I don't know why I'm trying to rationalize this. This is a fake example. But the market price for this contract is $9.17, we'll call it cents. The actual price is $8, and we'll call it 94 cents. Right? So before anything, base case, just because this is the way it works, you should lose, what is that? Just 18 cents? If I'm doing that math right? I think so. Yeah. 18, 16? I don't know. Whatever. It's not important. Before anything, you should lose money on this contract, regardless of the direction that it goes. Because even if you're right, and this contract goes from $9.16 to $10, well, you just left 18 cents on the table, right? You just left 10% of that trade, of that move on the table, a little bit more, almost 20 on the table. See how you just lost money on that trade? See how that wasn't a good trade? But then on this one, let's say these contracts go to $10. Well, you only really risked losing 48 cents when you think about it like that, because this contract should be worth 42 cents right now. So you're buying this for $9.16. It should be worth $9.42. You want to trade it to $10. Well, now you need so much more of that move, so much less of that move to happen. You see how you just set yourself up? Just same strategy of being bullish on the stock. However, these contracts are cheaper, even though they're closer to the money, so they should be more expensive dollar amount. Isn't that madness? Isn't that unbelievable? 17 and a half minutes. I can ramble on a little bit longer. That's the name of the game when you trade options. I am bothered deeply by this. Shouldn't really say that. I think it's awesome. I love working with this kind of stuff, but that is how this game works. If you can spot these options that are out there, if you could spot them, that's how you make money. Now, I forgot what I was going to say. Now, that's the name of the game. That's it. Whatever I was going to say totally jumped out of my head. I should really use scripts for this, but whatever. This was what I wanted to talk about in this episode, and this is an extreme example, of course, because I'm in a C++ file. I'm just modeling it, and I'm using a random number generator. But that's how it works. That's how stupid money is made, and that's how a lot of money is lost that nobody even knows about, right? I remember what I wanted to say. The average rule of thumb is that IV over 20% for 0.2 is considered expensive, a little more pumped up than other contracts. And so even just knowing that, you can notice that this contract is inherently cheap. Now, one thing that I think is an inherent flaw in the way I coded this is these strikes have the same IV, even though one's a call, one's a put. Now, it should, in the real world, it'll be different because it's a put, right? Because puts are inherently a little bit more expensive in these terms, so they're a little more juiced because they're insurance. People just will pay more for them because they need to be covered. They need to have their back covered, you know what I mean? But that's how this whole thing works. That's how options get mispriced. That's how implied volatility is calculated. And yeah, I hope that you guys learned something new. I hope that you enjoyed this video. I hope that if you're just a regular retail trader, you're going to pay more attention when you buy options. And I hope that if you're, I'm not even sure. I can't even believe that this is the way that we do this, right? If you go to Silicon Valley right now and you're like, I want to watch a rocket ship leave the atmosphere, they're like, pull up a chair. SpaceX is going to do it really soon. You're like, awesome. But then if you're like, I want to know the volatility of the stock, nobody has an answer, right? I think that's madness. I can't even believe it. But that's the video. That's the video. I gotta stop talking about it. Link to the code will be in the description. I'm not sure how many other resources I found for this. But whichever ones I found will be in the description. I have a business. That Twitter and that link will be in the description. My personal Twitter will be in the description. I hope you guys enjoyed this video. It was a little all over the place. I went a little off the rails, but I hope that you guys enjoy that side of it. My name is Joseph Garcon. Channel is called Ethan Network. I will catch you in the next one. Be well.